Welcome to MarineLearn, practical knowledge and training for maritime professionals. Hit the bell button, subscribe, and like the video so we keep bringing valuable content to you.
For a naval engineer, precision metalworking is an absolute requirement for operational survival while underway. A poorly fabricated part doesn't fail an inspection, it fails the ship. So what exactly separates a crude, manually drilled hole from a secure, naval-grade mechanical anchor capable of withstanding heavy sea states? This diagram illustrates the necessary starting point. Notice the cutting edge of the twist drill. That precise 118-degree angle is the foundational geometry required to initiate a cut in standard naval steel. Creating that mechanical anchor is a strict 4-phase operational sequence. We divide this progression into creation, refinement, function, and troubleshooting. Each stage demands its own dedicated tooling and exact mathematical tolerances. Think of this as an essential end-of-class review. We are going to cover the rigid rules of engagement for workshop tools. Mastering these sequential phases ensures that the components you fabricate will hold fast under the extreme mechanical stresses of a deployed vessel. Phase 1 is creation. This schematic breaks down the anatomy of our primary cutting tool, the standard twist drill. Look at the measurement at the very bottom. That 118-degree point angle is the absolute standard for general-purpose naval engineering work. We must safely deliver rotational power to the tool. This chart outlines tool holding methods. Notice the far right diagram. A Morse taper relies entirely on high-friction wedging action. The machine's rotational load forces the taper tighter into the socket. Breaking that extreme friction fit requires a specific procedure using a tool called a drift. Read the warning carefully. Never strike the drill shank directly. You tap the drift wedge, forcing the taper down evenly. Respecting the physics of that friction fit prevents catastrophic damage to the machine spindle, ensuring your tool survives Phase 1. Phase 2 is refinement. Here, we transform that raw, primary starter hole into an exact profile with tight tolerances. This hole finishing matrix illustrates the 3 primary shaping operations. We use countersinking for flathead screws, counterboring to sink socket heads flush, and spot facing to create a perfectly flat seat on a rough surface. When a hold requires exact tolerances, we move to reaming using this strict mathematical rule. Pay attention to the far right box. A standard twist drill always cuts a hole slightly larger than its stated diameter, typically by 0.05 millimeters. Because of that cutting behavior, you must calculate the drill size carefully to leave a very narrow margin of material, usually between 0.1 and 0.5 millimeters, for the reamer to actually shave away. Excessive metal will shatter the tool's delicate flutes. This warning graphic illustrates the primary constraint of reaming. Rotation must never be reversed. Rotating backward drags trapped chips directly underneath the cutting edges, which severely scores and destroys the mirror finish you just cut. Phase 2 leaves zero room for operator error. One single backward turn negates all of your previous precision work. Now we enter Phase 3, function. This diagram details the 3-piece tap set used for internal threading. You must use the taper, intermediate, and finally the bottoming tap in strict sequence to cut threads perfectly to the bottom of a blind hole. This graphic details the unique tapping rhythm. The right side panel shows the mandatory quarter turn back technique. After a full turn clockwise, you must reverse the tap a quarter turn to physically snap the metal chip you've just shaved off. Failing to break those chips cause them to pack tightly into the flutes. Eventually, they will bind, lock the tool, and snap the tap off flush inside your workpiece. External threading operates on similar limits. Here we see the setup for cutting threads on a rod using a split die and stock wrench. Before cutting, you must prepare the rod using the blank sizing rule shown on the right. When the hardened teeth of the die compress into the softer steel of the rod, the metal flows and physically expands outward. If you cut your blank rod exactly to the major diameter of the thread beforehand, that expanding metal has nowhere to go. It will bind inside the tool, overheat, and tear the freshly cut threads apart. Successful threading requires managing physical displacement. You must evacuate the chips internally and allow space for material expansion externally. The final phase is troubleshooting. This diagnostic matrix traces workshop failures back to physical causes. Look at the middle row. If your drill suffers a split web and cracks up the middle, the root cause is excessive operator feed pressure. This matrix for finishing and threading applies similar root cause analysis. The top row shows a torn finish results from turning a reamer in reverse. The middle row reveals that a binding elastic tap wrench is caused by packed chips twisting under tension. Every broken tool or ruined part stems from a specific error. It is never bad luck. It is a failure to respect the rigid physical geometries of the cat. This diagram shows the complete part progression. Action 1 penetrates using a 118-degree twist drill. Action 2 profiles with a counterbore. Action 3 shaves to tolerance with a forward-turning reamer. Action 4 taps internal threads, reversing to clear chips. You can test your own operational readiness against these strict, non-negotiable scenarios in this workshop assessment graphic. Strict adherence to these procedures is not a matter of personal workshop preference. It is dictated entirely by inescapable physical laws. In naval engineering, precision equals survival. Master the tool, and you secure the vessel.